Okay, hi, period 7 students. So this is going to be the conclusion of our lesson on motion. This was the example that I wrote up to close out the last video that I posted for you guys. So it's going to be another example where we look at motion, analyzing the graph of a function. In this particular case, we're going to look at the graph of the velocity function. Okay, so we're going to use the graph of the velocity function v of t to answer the following questions. All right, so for part A, question asks, when does the particle reverse direction? So we know that the direction of movement is dictated by the sign of velocity. Okay, so the particle is going to reverse direction where velocity changes sign either from positive to negative. That means the particle is going to go from forward to backward, or if velocity changes sign from negative to positive, it's going to go from backward to forward. Okay, so just to take a look at this graph here really quick, I'm going to highlight this portion of it, but if we were to talk about the direction of motion for our particle, velocity is positive on this entire interval here in yellow. So that means our graph is going to be moving forward at that time. Velocity is 0 on this highlighted interval in light blue. So that means that the particle is at rest at that point. Velocity is negative on this interval here in purple. So that means that our particle is moving backward. And then velocity is positive once again on this interval in yellow, which means we are moving forward. So that's going to answer like part C for us in this problem, but also helps us with part A. So the particle reverses direction. I think there's an optional answer for that. So I think that you could say that it reverses direction at time t is equal to 8. Okay, so that is where the blue highlighter meets the purple highlighter. Because the velocity is positive, so our particle is moving forward in the first 6 seconds, and then it's stopped for 2 seconds, and then our particle moves backwards. So if you want to include 8, I think you can make an argument for that. If you don't want to include 8, I think you can make an argument for that as well, because the particle is stopped for 2 seconds before it reverses direction. So if you don't think that it reverses direction at that particular instance, I could buy that argument as well. But the value that you do need to have is at time t is equal to 11. So that is where the highlighter in purple meets the highlighter in yellow. Okay, so velocity does go from negative to positive at that particular time. So the particle does reverse direction at that moment. Okay, part B. If we're asked to graph speed, we know that speed is the absolute value of velocity. So if we want to graph the absolute value of the velocity function, the graph of speed is going to look exactly the same as the graph of velocity, except for that highlighted piece in purple. Because velocity is negative there, we have to take the opposite of that portion of the function to make it positive. So we're going to take that highlighted portion in purple and reflect that graph across the t-axis. Okay, so if we were to graph speed, the graph of speed is going to look like this. So it's going to look exactly like the graph of velocity until we get to time t is equal to 8. Okay, so graphically speed is going to look like so. And then between 8 and 11, we're going to take that portion that lies below the t-axis and reflect it where it lies above the t-axis. Okay, so the graph of speed is going to look something like that right there. Okay, on to part C. So we already talked about this. When does the particle move forward? When does it move backwards? And when does it stay still? So the particle is going to move forward when velocity is greater than 0. Okay, so that happens when our graph lies above the t-axis. Okay, so it lies above the t-axis on the open interval from 0 to 6. And we can't include the endpoints of 0 and 6 because velocity is not positive there. Velocity is equal to 0 at that point. Okay, and then we're also moving forward on the interval from 11 to 12. We have to use a bracket at 12 because velocity is greater than 0 at that given point. Okay, so at t is equal to 12, the graph does in fact lie above the t-axis. Okay, we are moving backward. So we're moving backward when velocity is less than 0. So that happens when the graph lies below the t-axis. So that happens on the interval from 8 to 11. And then the particle is still when velocity is equal to 0. Okay, so that actually happens at time t is equal to 0. Okay, so a lot of times students forget to include that point, but velocity is 0 at t is equal to 0. Okay, at that point, the velocity graph lies on the t-axis. It's also 0 on the closed interval from 6 to 8. Okay, that's that highlighted segment in blue. And velocity is also 0 at time t is equal to 11. Okay, so we need to make sure we have all of those points included where our particle is still, where velocity is equal to 0. Okay, so on to part D. So part D, and I'm going to go ahead and flip my tablet for this just to give a little bit bigger view. So part D asks, when is the acceleration positive? When is it negative? And when is it 0? Okay, so we know acceleration is the derivative of velocity. Okay, and we know that the derivative measures the slope of the tangent line. Okay, so acceleration is going to be positive when our graph has positive slope. It's negative when the graph has negative slope, and acceleration is 0 when the slope is 0. Okay, so again, we want to determine the intervals for which this occurs. Okay, so acceleration is positive when the slope is positive, so that's going to happen on the interval from 0 to 4. Now, let's talk about this really quick. So at the endpoint 0 and also at the endpoint 12, if you want to include those endpoints on your interval, that's fine, okay? If you don't want to include those endpoints on your interval, that is fine as well. So I'm not going to include the endpoints on my interval, okay? But we know that we cannot include the value of 4 on our interval, because if we think about like what's happening to the velocity graph at t is equal to 4, there is a corner for our graph, and we know the derivative is not defined at a corner. Okay, so just to review this really quick, because we haven't talked about this in a while, when do functions fail to be differentiable? It happens at corners, at cusps, at vertical tangents, and at discontinuous points. Okay, so our discontinuous points are like holes, vertical asymptotes, jump discontinuities, and oscillating discontinuities. Okay, so we can't include 4 on that interval because the slope or the derivative is undefined at 4. Okay, so when else do we have a positive slope? We also have a positive slope on the interval from 10 to 12. I have to have an parenthesis at 10. The interval is open there because the derivative is not defined at that corner. And then at 12, if you want to use bracket or parenthesis, that is entirely your choice. Okay, so I'm going to use a parenthesis at that endpoint of 12. Okay, so the acceleration is going to be negative when the slope is less than 0. Okay, so when the derivative is less than 0, so when we have negative slopes on the interval from 4 to 6, and also on the interval from 8 to 10. Okay, and I can include none of those endpoints on my intervals because the derivative is undefined at corners. The function is not differentiable at those points. Okay, and then the acceleration is 0 when the slope is 0, and that happens on the interval from 6 to 8. Okay, on to part E. So part E asks, when does the particle move at its greatest speed? Okay, so when we look at the graph of speed, speed is the largest at that time, at this time, and at that time. Okay, and speed's value is 2 at all of those times. So the times for which that occurs are t is equal to 4, t is equal to 10, and t is equal to 12. Okay, so that's when our particle moves at the greatest speed. T is equal to 4, t is equal to 10, and t is equal to 12. Okay, so on to the next part, and I think this part's probably the most difficult part of this problem. Part F asks, when does the particle speed up and when does it slow down? Okay, so we want to determine when it speeds up and when it slows down. So based on what we discussed on Wednesday, we know a particle speeds up when velocity and acceleration have the same sign. So both velocity and acceleration can be positive, or both velocity and acceleration can be negative. And the particle is going to slow down when velocity and acceleration have opposite signs. Okay, so if we go and look at the graph of velocity, velocity and acceleration are going to have the same sign when both velocity and acceleration are positive, or both velocity and acceleration are negative. Okay, so what are we looking for on this graph for velocity to be positive? Velocity is going to be positive when this graph lies above the t-axis. Okay, and acceleration is going to be positive because acceleration is the derivative of velocity. Acceleration is going to be positive when the slope of the graph is positive. Okay, so one circumstance where we can be speeding up is where the graph lies above the t-axis with a positive slope. Okay, and it also can happen where velocity and acceleration are both negative. So for velocity to be negative, the graph has to lie below the t-axis. And for acceleration to be negative, the slope has to be negative. Okay, so when we look at the graph here, I know on the interval from 0 to 4, the particle is speeding up because velocity is positive, the graph lies above the t-axis, and acceleration is positive, the graph has a positive slope. Okay, the graph is also going to be speeding up on the interval from 8 to 10. Okay, so from 8 to 10, velocity is negative, the graph lies below the t-axis, and acceleration is negative, the slope is going to be negative. So both velocity and acceleration have the same sign. And then lastly, on the interval from 11 to 12. So on the interval from 11 to 12, both velocity and acceleration are positive. The graph lies above the t-axis with a positive slope. Okay, our graph is going to slow down when velocity and acceleration have opposite signs. So that can happen when velocity is positive, the graph lies above the t-axis, and acceleration or the slope is negative. And it can also happen when velocity is negative, the graph lies below the t-axis, and acceleration, which is the derivative, which is the slope, is going to be positive. Okay, so we know our particle is going to be slowing down on the interval from 4 to 6. So from 4 to 6, we have a positive velocity because the graph lies above the t-axis, and a negative acceleration because the slope is negative. And then we are also slowing down on the interval from 10 to 11. Because on the interval from 10 to 11, velocity is negative, the graph lies below the t-axis, and acceleration is positive, the slope is positive. Okay, so that's the best way for you to interpret speeding up and slowing down. But I'm going to give you another way that you can check to make sure that you've done this properly. So a quick way for you to check speeding up or slowing down is if your graph is moving away from the t-axis, that means that your particle is speeding up. If the graph is moving toward the t-axis, that means that the particle is slowing down. So I'm going to erase what I highlighted here really quick. Okay, so when is the graph moving away from the t-axis? It's moving away from the t-axis for these times here in yellow. Okay, so that's when our particle is speeding up. And the graph is moving toward the t-axis where I've highlighted, where I wanted to highlight in blue, which is here and here. So our particle is slowing down on those intervals. Okay, so last part G, asks us to graph acceleration, okay, which is essentially asking us to graph the derivative of the velocity function. Well, when we look at how many segments comprise the velocity function, there are 5 segments in total that do that, okay. So that's not what I wanted to have happen, but we'll fix it. So the graph of velocity was supposed to look like this. So there are 5 segments that make up that velocity graph. Okay, so this is segment number 1, segment number 2, segment number 3, segment number 4, and segment number 5. Okay, now if we recall like graphing derivatives, so ordered pairs on the graph of the velocity function are going to look like t comma v of t. On the acceleration function, they are t comma a of t, which we can think of that as t comma v prime of t. Okay, so the y-coordinate of every point on the graph of our derivative is just the slope of the graph of our function v. Okay, so what we want to do is we want to calculate the slopes of all 5 of those segments that we identified. Okay, so the slope of this first segment, we've risen 2, we've run 4, so that has a slope of 1/2. The slope of segment 2, it's risen -2 and run 2, so that has a slope of -1. For segment number 3, that has a slope of 0. For segment number 4, we've risen -2 and run 2, so that has a slope of -1. And for segment number 5, we've risen 4 and run 2, that has a slope of 2. Okay, so once we have the slopes for each of those segments, that's going to give us the y-coordinates for all of those points in between those t values. Okay, so in between the t values of 0 and 4, the slope is 1/2. So that means that the y-coordinate of every single point between 0 and 4 is going to be 1/2. Now, our starting point over here at t is equal to 0, if you want to use a closed dot or an open dot, it does not matter. Okay, but at 4, if I am graphing the derivative, I have to have an open dot on the graph of the derivative because the velocity function v of t has a corner, and we know derivatives do not exist at corners. Okay, so the second segment has a slope of -1, so in between the t values of 4 and 6, the y-coordinate is going to be -1. So we have to have open dots at the 2 endpoints because your graph has corners at those values. Okay, between the t values of 6 and 8, the slope is 0. So that means the y-coordinate on the acceleration graph is going to be 0. Between the t-values of 8 and 10, the slope is -1. So between 8 and 10, the y-coordinates on the graph of acceleration are -1. And then between the t-values of 10 and 12, the slope is 2. So between the t-values of 10 and 12, the y-coordinate is going to be 2. So we have to have an open dot at 10. At 12, it's your choice whether you use an open dot or a closed dot. Okay, I'm just using an open dot at the two endpoints as well. Okay, so I think that's a good problem. It illustrates some of the stuff that we've talked about earlier on in the lesson. It's just we're looking at it in a different context. This time we were looking at it in the context of analyzing a velocity graph. Okay, so that's it for the lesson on motion. And we'll see you guys in class next week. Take care.